Okay, everybody, this is the current divider rule. So we've seen the voltage divider rule, and that was how we found the individual voltage drop over resistors. The current divider rule is what we use to find how much current goes through different branches inside of a parallel circuit. So we know that we'll have some sort of current coming in this lane here, so a few electrons coming in through here, and each of them are going to split off into these two separate paths, like so. And they'll travel through this resistor and then come back and meet here. And the same goes for this side as well. They travel through here and come back and meet around here. Now, what determines how many electrons move through each of these branches is the individual resistances on each side. So obviously, electrons like to travel through the path of least resistance. So if we say our resistor 1 is 1 ohm and our resistor 2 is 2 ohms, we would expect more electrons to travel through the path of resistor 1, so through here, because it has half the resistance of R2. And specifically, we would actually expect twice as many electrons to travel through R1 than R2, because its resistance is half of R2. So, what this looks like as a formulaic rule is the current, let's say for some unknown resistor, just IX, is the total current coming into the original branch here. So we'll call this I source. So it's IS times the opposite resistor to the one we want to know in the branch. So if I want to know the amount of electrons going through R1, then I use the resistance of R2 over the total resistance of the two here. So that will be R1 plus R2. And I might, just for clarity's sake, make that a 1. So let's calculate the actual current going through I1 with the resistances we're given. I1 is the amount of current traveling through this branch up here. And that's going to be equal to the source current, which we'll say is 5 amps, which will be 5 times our resistor of the other resistor. So if I'm looking for the resistance through the branch of R1, then in my formula on top, I use the other resistance, which in this case will be R2, which has a value of 2 ohms. So it'll be 2 over the sum of the two, which will be 2 plus 1. Now that equals 10 on 3, or 3.33 amps. Awesome. Now what about the current through I2? Well, I2 will be the source current that we started with coming into the original branch here, and then we use the opposite resistance. So that in this case is R1, as we're looking for the branch through R2. So that will be 1 on top over the addition of the two resistances here. And that will be 5 on 3, which equals 1.67 amps. Cool. That is current divider in a nutshell. And the only way they can kind of spice this up a little bit is if you had a circuit with 3 branches instead. So what if we had 3 resistive branches like this? Well, we can see our original rule here only accounts for 2 resistances, R2 and R1. So what we would have to do to use the current divider rule is combine, let's give these some labels, so this will be R1, R2, and R3. What we would do is if I wanted to know what the the current through R3 was I could just use my parallel addition of 2 resistors to collapse this down to a circuit that looks like our original, like so, where this here is R3 still, and this is going to be the parallel combination of R1 and R2. So, let's quickly calculate what the parallel combination of R1 and R2 is. So R1 in parallel with R2 is the multiplication of the two on top, R1 times R2, over the addition of the two in the bottom. That's the shortcut parallel combination rule. So that will be R1 was, let's have a quick peek, what did we make that? 1 and 2. And we'll let R3 be 1 as well. Like so. So, R1 and R2 in parallel is going to be R1 times R2, which is going to be 2 over R1 plus R2, which will be 1 plus 2. So it'll be 2 on 3 ohms. So what our resistor here has now become is 2 on 3 ohms, with R3 remaining as 1 ohm. So now it becomes the exact same case that we had before. We have our source current coming in the base here, which we can say is still 5 amps. And we know it will branch off into each of these paths depending on the resistance of the two branches. Let's now work out what our current flowing through R3 would be. I3 is going to be equal to our source current, which is 5 amps, times the opposite of the one. So if I'm looking for the current going through R3, I look at the resistance of the opposite branch, which in this case is 2 on 3, over the addition of the two, which is 1 plus 2 on 3, like so. And this is equal to 2 amps. What I want to do really quickly before this video is over is show an actual circuit analysis question that you're more likely to get asked. So, what we're asked here is for the above circuit in this top right corner, we're asked to find the current through the 2 ohm resistor. So we need to find this little I here. So, our first step is we need to find our source current, or what is the current going into all 3 of our resistive branches here. So, to find that, we need to do a little bit of simplification and collapse all 3 of these resistors down into one resistor. And that way we'll have a simple VIR circuit. Let's do that. What we want to do is collapse all 3 of those resistors, so we'll use the resistor parallel addition rule, which is R total is equal to 1 on R1 plus 1 on R2 plus 1 on R3, all to the power of minus 1, which equals 1 on 1 plus 1 on 2 plus 1 on 1 to the power of negative 1, which is 2 on 5 ohms. Awesome. So now we have a circuit that is equivalent to this circuit here, where we have a plus minus with 1 resistor here. And this has a value of 2 on 5 ohms, and this is still 4 volts. Awesome. So let's just use our Ohm's law, V equals IR, to rearrange for the current going through this circuit. So what is this current going through this loop here? Well, rearranging this, we get I equals V on R, which equals 4 volts over our resistance, which is 2 on 5, and that equals 10 amps. So awesome, we just found our big I up here, the current going into our 3 resistive branches, and that was 10 amps. So now is the important part, and that is using the current divider to find out what the current going through the 2 ohm branch is. So remember, we're trying to find just through this 2 ohm branch here. So like previously mentioned, we need to collapse the other 2 resistors, the 1 ohm and the other 1 ohm, into a single resistor so that we can use the current divider rule. So let's do that. We want to find what is 1 ohm in parallel with 1 ohm. Well, that's going to be 1 times 1 over 1 plus 1, which equals 1 on 2 ohms. Cool. So now our circuit, coming from this original one, looks like this. We've still got our 4-volt battery source, only now we have our 2 resistors, where one is still the, I'll do that in a different colour. One is still the 2 ohm resistor that we're trying to find the current through, and this other resistor is the parallel combination of the 1 and 1, which we found to be 1 on 2 ohms. It doesn't matter which way around these are. So, we now use our current divider rule, which is I going through the 2 ohms is equal to our source current, which we found to be 10 amps. So 10 times, remember if we're trying to find the current through our 2 ohm branch, we use the 1 on 2 ohms, the other resistor on the top of our fraction here. 1 on 2 over the addition of the 2. So 2 plus 1 on 2. And that equals 1 on 3 amps. So there we go. We just found the little current I from our original circuit to be 1 on 3 amps. And you can repeat that process the exact same way for the other 2 branches as well. So thank you very much. I hope you enjoyed.